Hello and welcome to yet another lecture on basic electrical engineering, paper code ESEE101. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is working principle of a three-phase induction motor, significance of torque slip characteristics, loss components, and efficiency. Lesson objective. After end of this topic, students will able to understand the concept of working principle, synchronous speed, slip, torque slip characteristics, power flow diagram, relationship between rotor power and losses of a three-phase induction motor. So working principle of a three-phase induction motor, significance of torque slip characteristics and loss components and efficiency. So the contents, that is, today I will discuss about the working principle of a three-phase induction motor, synchronous speed, that is N suffix S, NS we can say, of a three-phase induction motor, slip of a three-phase induction motor, torque slip characteristics, power flow diagram, relationship between rotor power and losses, related problems. We will discuss some problems in order to understand that what we have discussed today. So, first of all, we will start with working principle of a three-phase induction motor. So, from our previous discussion that we have done in our previous discussion, it is clear that if balanced three-phase voltage are applied to three isolated stator coil separated by an angle of 120 degree in space, a rotating magnetic field that is nothing but an hypothetical NS pole that is rotating at a particular speed comes into play. So in our previous discussion, we have already seen that when a three-phase balanced voltage are applied to the three isolated stator coil, they are separated by an angle of 120 degree each space, a hypothetical north and south pole, or in other words, you can say a rotating magnetic field that is generated and it is rotated at a particular speed. So initially, the rotor is not rotating. So due to the flux cutting, a EMF is induced in the rotor conductor. Again, we have already seen that rotor terminals are shorted either by the end rings or by the resistance. So current due to this induced EMF begins to flow through the rotor conductor. So this current, that is according to the Lenz's law, will oppose the region due to which it comes into play or due to which it exists. So this rotor current is there because of the rotor induced EMF. So rotor try to do something so that the rotor induced EMF will not be there. In order to do that, so what is the process? The process is rotor begins to rotate in the direction of rotating magnetic field at a speed close to the speed of the rotating magnetic field but not equal. So in order to do this, rotor started to rotate in the direction of the rotating magnetic field at a speed that is close to the speed of the rotating magnetic field but not equal to the speed of the rotating magnetic field. To reduce the relative speed between the rotating magnetic field and the rotor. That is, in order to reduce the flux cutting. Rotor begins to rotate in the direction of the rotating magnetic field. So from that particular discussion, we will see that there are two speeds are there. One is the speed of the magnetic field, is the speed of the rotating magnetic field, which is also known as synchronous speed in suffix s, and another speed is the speed of the rotor, that is in suffix r. And it is clear from the discussion that in s, is the synchronous speed is always greater than the in r rotor speed for three-phase induction motor. So now, as a user, there are three terms that is associated with that particular discussion, that three-phase induction motor. There are three terms. One is called the three-phase, another is called the induction, and another is called the motor. So we will see that why it is called three-phase induction motor. So from the discussion, now as a user, what we will see, we see that the machine that is firing mechanical output by rotation, where we are inputting to the machine electrical energy is inputting as an input. So the machine by rotation firing the mechanical output, where the electrical energy is given to the machine as an input. So as a result, this is generally known to us as a motor. This is generally known to us as a motor, where the mechanical energy is converted into, where the electrical energy is converted into the mechanical energy. Input electrical energy, output mechanical energy by rotation. So it is the conception of motor. So one part that we have discussed, why it is called the motor. Now the second one, why it is called the three-phase. Because the motor that is takes the three-phase voltage, so the motor is the three-phase motor. The motor that is taking the three-phase voltage, so it is called the three-phase motor. And another part that we have laid is the induction part. So it is clearly that the discussion that we have done from that, it is clear that it is operating on the principle of induction. So combine those three, we can call this motor is a three-phase induction motor. So another conception of three-phase induction motor is the synchronous speed that is given by Ns, N suffix s, of a three-phase induction motor. So the synchronous speed, it is known that we have already seen that synchronous speed is the speed of the revolution of the magnetic field in the stator winding of the motor. The speed of the rotating magnetic field in the stator winding of the motor is known as synchronous speed in S. It is the speed, it is the speed at which the electromotive force is produced by the alternating machine is known as synchronous speed. So let us take a particular diagram. So here there is a two poles. This is a stator and there is a two poles, north and south. This is the stator and this is the stator poles. And here this is the rotor section. It is in a rotating. So here the two pole is shown, and it is clear that one complete cycle has covered the two poles. So from the figure, it is clear that two stator poles covered one cycle of the rotating magnetic field. One complete cycle is covered by the two poles. So if we have p number of poles, so the if there are p number of poles in the stator, so it will cover the p by 2 cycle of rotating magnetic field. So one full revolution or one full rotation of the rotating magnetic field means when a magnetic field is rotating, so it will cover all the p poles. That is one full revolution of the rotating magnetic field. There are p by 2 cycles of the rotating magnetic field. So it is clear that one complete cycle requires two poles. So if there are p poles or stator poles are there, that is covering the p by 2 cycles of the rotating magnetic field, and one complete revolution of the rotating magnetic field means it will cover the p poles. So one full revolution of the rotating magnetic field, there are p by 2 cycles of the rotating magnetic fields. So as the rotating magnetic field that is rotate at a synchronous speed, that is ns, it will be in rotation per minute, rpm equal to ns by 60 rotation per second, rps. So 1 second number of complete cycles are is the only multiplication of p by 2 into ns by 60, it is tns by 120. So again, the number of full cycles per second is the frequency. So this will be give the conception of frequency. Frequency f equal to pns by 120. From that we will calculate or that the synchronous speed ns equal to 120 f by p. So the synchronous speed n is equal to 120 f by p. This is called the synchronous speed in f 120 f by p. So we are taking an example where we are setting that number of poles p equal to 2, frequency is 50 hertz. So what is the value of synchronous speed in rpm? That is 120 f by p. It is 120 into 50 by 2, that is 3000 rpm. So for the different poles, say number of poles 2, 4, 6, 8, 12. For the different frequencies 50 hertz and the 60 hertz, we will calculate the synchronous speed. That is 3000, 1500, 110, 1000, that is 1000, 750, 500. For the 60 hertz, it is 3600, 1800, 1200, 900, and 600. This is the table that we have from for the different poles and the different frequencies. We have calculated the synchronous speed. So another conception is the slip of a three-phase induction motor. It is clear from the previous discussion that there are two speeds that we have seen. One is the speed of the rotating magnetic field, that is called the synchronous speed, that is 120 f by p, the mathematical calculation. And another is the rotor speed, that is called the nr. And it is clear from our discussion that the speed of the rotating magnetic field, that is in s, is always greater than the speed of the rotor, that is called the nr. So in a three-phase induction motor, stator of the motor will generate rotating magnetic field or RMF, that is rotating magnetic field, because of the phase shift with 120 degrees with the three-phase supply input that we have already known. RMA, that is revolves with the stator of its own speed, which is known as the synchronous speed, and it is denoted with ns, that is also known to us. The rotor of the motor, that is begins to revolving with the speed which is known as actual speed or the speed of the rotor, that is in r. Actual speed of the machine or the speed of the rotor, that is in r. So sleep is a speed among the rotary magnetic flux as well as rotor, expressed in terms of for every unit synchronous speed. It can be measured in dimensionless, and the value of this motor cannot be zero if the revolving flux, synchronous speed, and the speed of the rotor are in S and in R in the rotor. The speed among them can be equivalent to ns minus nr. It is the relative speed between them. So the speed can be expressed as s equal to ns minus nr by ns. So this is the general mathematical expression of the speed. S equal to S stands for sleep and S equal to in S minus in R by in S. From that, we can easily calculate the value of rotor speed or the speed of the machine, that is in R. So in R will be, from that particular calculation, we will get in R will be 1 minus S in S. So in R will be 1 minus S into in S. From that particular equation, we will get the value of in R. Now, that is the actual speed of the machine. Just take the calculation and we will get that the value of in R. So this is the general conception of speed that we have already known. And it is clear that it is a ratio of speed. So you can write that it is a dimensionless. It is a dimensionless unit. Now, there are different importance of sleep in the induction motor are that when the sleep value is zero. From that mathematical expression, when the sleep value is zero means in R in S equal to in R. So, if the sleep value zero, then the speed of the rotor is equivalent to revolving magnetic flux. So there is no motion among the coils of the rotor as well as the revolving magnetic flux. So there is no flux cutting act in the rotor coils. Therefore, EMF will not be generated within rotor coils for generating rotor current. So this motor will not work. So it is essential to have a positive value in this motor, and due to this reason the sleep will never become zero in an induction motor. So another is that when the sleep value is 1. So when the sleep value is 1, NR is 0. So the sleep value 1 means the rotor in the motor is stationary. This is called the standstill condition of the rotor. Now when the sleep is minus 1 or say, so when the sleep is minus 1, the speed of the rotor in the motor is more. So when in this case, when the sleep is negative, it means in R that is greater than the in S. So the speed of the rotor in the motor is more comparable with the synchronously revolving magnetic flux. So this is possible only when the rotor within the motor is turned in the revolving magnetic flux direction using the help of the prime mover. So it means that with help of some external prime mover, uh, with the help of some external prime mover, the rotor that is run about the beyond the synchronous speed. So this is the general conception of induction generator. This is the condition when the motor operates as an induction generator. And when the sleep value is greater than 1, so the sleep value of the motor is greater than 1, then the rotor will turn in the opposite direction of the revolution of the magnetic flux. So the magnetic flux is revolving in the clockwise direction and the rotor will turn rotating in the anti-clockwise direction. So NR became minus NR here. So the speed among them will be like in S plus NR. This is in braking or plugging of this motor. The sleep is greater than 1 is attained to rapidly bring the rotor of the motor at the rest condition to bring the rotor and of the motor at rest condition. So for the different values of slips, we will obtain the different conditions of the induction motor, three-phase induction motor. So this is the general formula of the slip that we have known. Slip is given in the percentage, it is given ns minus nr by ns into 100%, where nr is the synchronous speed and ns is the synchronous speed and nr is the rotor speed. So let us take an example to calculate slip in the motor where the synchronous speed is given ns equal to 1300 rpm and the actual speed is given that is 1300 and the synchronous speed is nr is 1250 that is given. So the value of the slip that we have calculated, that is nr minus ns, that is the speed, relative speed, that is 50. So the value of slip, that is nr minus ns, will be given by 3 by ns into 100, that is the slip value is 3.84%. So while designing the induction motor, measuring of the slip is essential. For that, the above formula is used to understand how to get the difference as well as the percentage of slip. This is a normal calculation. So now we will come to the torque slip characteristics. This is the main part, that when we draw a graph or a curve between the torque and the slip from start, when it is at a starting condition, that is nr equal to 0 and the value of the slip is 1, and to the synchronous speed when nr equal to ns, the value of slip is 0. It's all the torque slip characteristics of a three-phase induction motor. So this is the torque equation, that when the input voltage is constant, the torque is proportional to slip square e2 square r2 plus r2 square divided by r2 square sx2 square. This is the e2 s into e2, that is generally the secondary voltage that is induced in the three-phase induction motor, and where the R2 and X2 stands for the resistance and the reactance at the secondary side. This is all the rotor torque. So when the input voltage is constant, this portion, that is the voltage, is constant, so it is become torque is proportional to SR2 divided by R2 square plus SX2 square whole square. So this is the general torque slip characteristics, where this region I will discuss in the next slide why this relation is coming. So just only see that OA is the stable region, this one. AB, that particular part, is the unstable region, and this is the value of the maximum torque, and at slip S equal to Sm. This is the value of starting torque. This is the value of starting torque at point B. Starting torque. This value, this is the torque along the y-axis and slip along the x-axis. So here the value of n equal to ns, slip is 0 and slip is 1. For that particular, we have drawn a torque slip characteristics, and where OA is the stable region, AB is the unstable region, point A is the maximum torque, point B is the starting torque, and point C is the full load torque. So we will now discuss the particular thing. So torque has three regions. One is called the stable operating region that we have already seen. One is called the unstable operating region that we have seen, and another is called the normal operating region. So stable region, that is the OA region that we have seen. For the stable region, it is clear that the slip is very small. The value of the slip is very small. So now, if the slip is very small, we can omit that particular part. Sx2 square is much less than r2 square. Hence, we can easily neglect the Sx2 square. So the torque that is from that particular torque equation that we have made, The torque is proportional to S R2 by R2 square. So where R2 is constant, so torque is proportional to S. In this region where the load is increasing means torque increasing and the slip increasing. And characteristics is approximately a straight line, that is a y equal to mx graph. A straight line passing through the origin for a small value of the slip. That is why it is a y equal to mx graph. From that particular torque equation, we will obtain the torque slip characteristics. So that is the particular y equal to mx graph from O to A, and this is called the stable region OA for the low value of the slip. Where the load increases means torque and the slip both are increases. So the unstable region, that is the AB. When the AX, that is, increases significantly, so the value of the S is the further from SM the region is unstable region. When S is high between SM and 1 that we have already seen in the graph, R2 square can be neglected as compared to S2 square. It's S2 square into X2 square. So we are neglecting the R2 and the torque that is became proportional to 1 by X, where the X2 is constant. In this region, the load increase means slip increase, but torque is increase. Load increase, slip also increase, the torque decrease. Because when loading is increased, the value of NR is going to increase actual speed of the machine. So as a result, the difference between NS minus NR goes on increasing. So as a result, the slip also increasing, but the torque, as the slip increase, the torque decrease. This is the general conception of torque proportional to 1 by S, that is the conception of rectangular hyperbola. When the load further increase, the N will be decreased, speed will be decreased, S will be increased, leads motor to the standstill condition. Hence, motor should not be operated at any point in this region where torque is proportional to 1 by S, and the nature of the torque slip characteristics is rectangular hyperbola. That is the region AB where the nature is rectangular hyperbola from Sm to S equal to 1. When S equal to 1, this is known as the standstill condition, and it is going to reach at the standstill condition. And in this region, the motor is not in the operating condition. So from O to A, this is called the stable region, where it is following the y equal to mx graph. From A to B, it is following the rectangular hyperbola where torque is proportional to 1 by S. Another is the normal region, there is a low slip region, the motor can continuously operate in this region. So there are three torques that we have seen. One is called the starting torque. T suffix is T, ST stands for starting. One is called the maximum torque or pull out torque, that is TM. And one is called the full load torque, that is TFL. So starting torque, that is TST. The motor produces the torque when the S equal to 1 and the speed is 0. This is known as starting torque. Another is the maximum torque or pull out torque, that is known as TM. The torque that should be produced at S equal to Sm, it's the maximum speed, is called the maximum torque. Sm is the S equal to Sm, that is the maximum slip. Sm is the slip at which the maximum torque occurs. It is also known as breakdown torque or pull out torque. And another torque, it is called the full load torque. There is the characteristics, the torque that is corresponding to the point C is called the full load torque of the motor. Usually TFL is less than TM. So there are the three torques. One is called the maximum torque, one is called the full load torque, and the maximum torque corresponding slip is the maximum Sm. This is called the starting torque, and this is called the full load at the point B, the starting torque, and at the point C, the full load torque. So we will discuss about the three different torques. So now we will come to the losses in a three-phase induction motor. So losses are generally the three-phase. There are three losses. One is called the magnetic loss, that is the constant loss. One is the mechanical loss, that is the constant loss, and one is the electrical loss, that is the variable loss. So the magnetic losses are also known as core loss and the iron losses. Losses occur in the stator core and the rotor core because of rotating the magnetic field. And there are two types. One is called the eddy current loss and one is called the hysteresis loss. The hysteresis loss is occurred due to the alternating change in magnetic field in the stator core, and that can be minimized by selecting high-grade silicon steel as the material. And that is called the eddy current loss, that is occurred due to the flow of eddy current through body of the stator core. Can be minimized by using laminated construction of stator core. So the two losses that we all know that this eddy, we have already seen that the eddy current loss and the hysteresis loss, those two losses are dependent on supply frequency. If the frequency of the stator is equal to frequency of the supply, hence iron loss for the stator is more. If frequency of the rotor is much less, its iron loss is also very small, neglected under running condition. Mechanical loss, that is consist of frictional loss and the windage loss. The losses are much less due to speed drop is very small. Constant loss, that is the summation of iron loss and the mechanical loss. Another part is the electrical losses, that due to the resistance of the stator and rotor winding, the stator and the rotor copper loss and the I square R loss are the generally known as electrical loss. When loss goes on increasing, the current also increasing, so the variable losses, that is the rotor copper losses, are equal to 3I2 square R. 3I2 square R. So this is the general power flow diagram that we will see. A three-phase AC source, that is the from there input power is given. When an input power is given to the stator winding, stator has some stator copper loss and the stator core loss. After subtracted that stator core loss or stator copper loss from the PI, we are getting a PG, that is the air gap power. That is the power between stator and the rotor. There is the air gap is there, that we have already seen our previous discussion, that between the stator and the rotor there is an air gap is there. So the input power, when the stator core loss and the copper loss is subtracted from the input power, we will get the air gap power. From that air gap power, the next part is the rotor. We subtracted we minus the rotor copper loss. From there, we will give the mechanical power developed, and the mechanical power developed is transferred to the shaft. From the shaft, the friction, windage, and the stray loss is minus, and we will get the output power. This is the basic power flow diagram that we have to know. That is the input power. From the unit input power, we will subtract it or minus the stator copper loss and stator core loss. From there, we will get the air gap power. From the air gap power, we will minus the rotor copper loss to get the mechanical power developed. From the mechanical power developed, we will minus the friction, windage, and the stray loss in the shaft, and we will get the output power. This is the basic power flow diagram of three-phase induction motor. So now, from the power flow diagram, induction motor converts electrical power into mechanical power that we have already known. So three-phase supply is fed to the stator. Input power, that is root 3 VL IL cos phi, and this is generally known to us. We have done in our previous discussion why it is root 3 VL IL cos phi. So losses occur in the stator called stator losses, that is given by PSL. Remaining power, that is transferred to the rotor magnetically. It is called the output of the stator or input to the rotor, that is P2 equal to P in minus PSL. So the output from the stator will be input to the rotor, and it is given as P2 equal to input power minus PSL by SL, which stands for the losses occur in the stator core loss, and the stator copper loss that we have already seen. Now in the rotor side, there is a rotor copper loss is there. So that is PCU. Normally, the rotor iron loss that is very small, therefore it should be neglected. So the remaining part is called the mechanical power developed. That is the rotor input minus rotor copper loss. So rotor copper loss, that is PCU, is equal to 3I square R square. So here the mechanical power developed, that is P2 minus PCU, means P in minus PSL minus PCU. So the input power to the rotor minus rotor copper loss will give the mechanical power developed PM that we have already seen from that particular diagram. That is input power to the rotor, that is PG or P2, we can already say. That is PG or P2 equal to PI minus all the losses in the stator. Then PG minus rotor copper loss will give the PM. From PM, P suffix M will, that is the mechanical power developed, will minus the friction and windage and the stray loss, we will get the output power. So due to the rotating part in the motor, mechanical losses are occurred. So the output power is PM minus PML, that is called the, due to the rotating of the shaft, in the shaft there is the mechanical losses. The mechanical losses are friction loss, windage loss, and the stray loss that we have already discussed. So in the shaft, this PM minus these losses equal to output power. So P output is the PM minus PML. So the rotor efficiency can be calculated as rotor output by rotor input, where rotor output is the mechanical power PM and rotor input is P2. Rotor efficiency is the mechanical power output at shaft divided by electrical power input to the stator, that is P out divided by PM. It is called the motor efficiency, and this is called the rotor efficiency. It is deal with the rotor power input and the rotor output and rotor input, and it is the motor efficiency is the mechanical power output at the shaft and the electrical power input to the stator. So relationship between the rotor input, rotor copper loss, and gross mechanical power, that is P2, PCU, and PM. So in general, the relationship between the power in terms of torque is P equal to PG into omega T into omega. So omega can be written as TG into 2 pi n by 60. N is the speed of the motor. So the power that is transferred from stator to rotor are P2 that we have already seen. It is TG into omega s. It is TG into 2 pi ns into by 60. Here omega s because it is transferred from stator to rotor, and the speed of the rotating magnetic field at rotor is synchronous speed. So power generally is the multiplication of torque into omega, the angular speed. So gross mechanical power that is developed, so the gross mechanical power that is developed by the rotor Pm equal to Pg into omega, it is Pg into 2 pi n by 60. So the rotor copper loss, that is the PCU, that is P2 minus Pm, that is given by Tg. Just putting those values there, it is Tg into 2 pi by 60 ns minus n. So again, when PCTU by P2 is just dividing those two things, we will get ns minus n by s equal to s. So PCU by P2 equal to s, PCU equal to s into P2. So P2 equal to PCU by s. So what is PM? PM, that we all know, mechanical power developed, that is P2 minus PCU, that is the power input to the rotor minus copper loss in the rotor. So here the rotor power input is the copper loss by S. PCU, that is the copper loss, is equal to S into P2. P2 is the power input to the rotor. So just putting those values, we will get Pm equal to 1 minus S into P2. So PCU by PM, just putting those values, we will get S by 1 minus S. So also P2 equal to Tg into 2 pi Ns by 60 that we have already seen. So Tg equal to P2 into 60 by 2 pi Ns. So Tg is proportional to the Pt. P2. So Tg that is proportional to P2. So the torque in the synchronous watt, that is PSW equal to P2 equal to PCU by S, just putting those values equal to PM by 1 minus S. So this is the relationship between the different power flow in the three-phase induction motor. So the first problem is a 6-pole three-phase induction motor develops a power of 22.38 kilowatt, including mechanical losses, which total 1.492 kilowatt at a speed of 950 rpm on 550 volt 50 Hz mains. The power factor is 0.88. Calculate for this load. The first is the slip, second the rotor copper loss, the total input if the stator losses are 2000 watt, the efficiency, the line current, the number of complete cycles of the rotor electromotive force per minute. So when we are approaching to a numerical problem, we will keep in mind that all the voltages and the currents that are provided in a problem, they are all the line voltages and the line current, and the power that is given are the output power. So when a power is given, it is the output power. It is given the number of poles, that is P equal to 6. PM, that is the motor develops a power of 22.38 kilowatt. PML, that is the mechanical losses, that is 1.49 kilowatt. N is the speed of the motor, that is 950 rpm. V, that is the line voltage, is given 550 volt. Frequency is given 50 hertz, and the power factor, that is cos theta, is given 0.88. So first is the calculation of the slip. So formula of the slip is Ns minus N by Ns. So we have to find the Ns, that is the synchronous speed. It is 120 m by p rpm. So just putting those values of f and p, we will find it is 1000 rpm. So the slip is 1000 minus 950 by 1000, that is 0 0.05. 0.05. So the rotor copper loss, that is PM, that we know the formula of PM equal to P2 1 minus S. So from there we can easily find the P2 where PM value is given. Just putting the value of slip here, we will get the value of PM, that is 23.55 kilowatt. Copper loss, that is S into P2, just putting those values, it is 1.17 kilowatt. S value, that slip is 0.05 and P2 is 23.55. It is 0.05 into 23.33. That is 1 point or 23.55, that is 1.17 kilowatt. So the total input, that is P in, that is P2 plus stator losses, that is 23.55 plus 2, it is 25.55 kilowatt. The efficiency, that is output power, is PM minus PML, just 22.38 minus 1.492, that is 20.88 kilowatt. So the percentage of efficiency, that is P out by P in into 100, just putting those values 20.88 by 25.55 into 100, that is 81.8%. And that is the line current. I have already told that P in, that input power equal to root 3 VL IL cos phi. So IL equal to P in by root 3 VL cos phi, that I have told all the values are given in the line. So just putting those values of VL and cos phi equal to 0.88 and the value of P in is 255.55 into 10 to the power 3, we will get the current 30.4 ampere. The number of complete cycles of the rotor electromotive force per minute, that is Fr, it is Fr equal to S into Fs. So S value is 0.05 into 50, that is 20.5 hertz per second, and for the 60 it will be 2.5 into 60, that is 150 hertz per minute. So the another problem is that a 37.3 kilowatt 4-pole 50 hertz induction motor has a friction and windage loss of 320 watt. The stator losses equal to rotor losses if the motor is delivering full load power output at a speed of 1400 rpm. Calculate synchronous speed, sleep, mechanical power developed by the motor, rotor copper loss, power transfer from stator to rotor, stator power input, efficiency. So data that is given that the output power is 37.3 kilowatt, poles are 4, F equal to 50 Watt, friction and windage losses, the PML that is 33020 watt, stator losses and the rotor copper losses, and it is given N equal to stator losses PSL, rotor losses PCU, because it is given that the stator losses are equal to rotor losses, so stator losses PSL equal to rotor losses PCU and N equal to 1400 RPM. So synchronous speed N is equal to 120 F by P RPM. Putting the values of F and P here, you will get 1500 RPM. Sleep, that is S equal to Ns minus Nr by Ns. Just putting those values of Ns and Nr in this equation, we will get the value of sleep is 0.04 or the 4%. So the mechanical power developed by the motor, that is the output power, is Pm minus PML. So mechanical, that is P out plus PML. So this that I have already told that any data that is given in a problem, it is given at 37.3 kilowatt, means the output power of that motor is 37.3 kilowatt. Any data that is given in a problem is when a power is given, that is output power. When a voltage is given or a current is given, that is line voltage and the line current that we have seen in our previous problem. So just putting those values, and it is 3320 watt, that is 3.320 kilowatt, that is 40.62 kilowatt. The rotor copper loss, that is PCU by PM, is S minus 1 by S. Just putting those values, we find the PCU. But sleep is 0.04 that we have just calculated, is 1692.5 watt. Power transfer from stator to rotor, that is the P2, that is P2 equal to PM plus PCU, that is 40.62, that is the mechanical power, plus 1.692, that is 42.312 kilowatt. Because P2, that is the power that is transferred to the rotor, minus the rotor copper loss, will give the mechanical power that is developed. So the stator power input, that is P in, that is output of the stator plus the stator copper loss, and it is equal, that we have already seen that it is equal to the rotor copper loss, and its value is 1.692 from that particular equation. That is the stator loss is equal to the rotor loss, so it is calculated 1.692. 1.6925 kilowatt. So just putting those values, you will find 44.0045 kilowatt. Here it is that SL equal to PC equal to 1.6925 kilowatt. So the efficiency, that is P out by P in into 100, that is 37.3. The output power, the input power is just calculated 44.0045 into 100, that is 84.76%. So another problem, that is 18 kilowatt 4-pole 50 hertz 3-phase induction motor has friction and windage loss 500 watt. The full load slip is 4%. Compare full load. Compute for full load rotor copper loss, rotor input, the shaft torque and the gross torque. So output power is given 80 kilowatt. Again, it is given finding from the problem. Pole is 4, frequency is F, PML given that the windage and the friction loss is 50 watt and slip is 4%. So the rotor copper loss, that is we have to calculate, that is PM, that is P out plus PML. Just summing that, we are finding the PM. So what is the rotor copper loss? That is PCU equal to PM into S by 1 by S minus S, that is PCU. Just putting those values. The value of slip is 0.04, 4% is 0.04. It is given the copper loss is 770.83 watt. So the rotor input, that is P2 equal to PM plus PCU, that you already know. Just putting those values, we will find that 19270.83 watt. The shaft torque, in order to find the shaft torque, we will find the synchronous speed Ns equal to 120 F by P. Just putting the values of P and F, we will get 1.00 RPM. In R, that is the speed of the actual speed of the motor, that is Ns into 1 minus S, that is 1500 into 1 minus 0.04, that is 1400 RPM. So the shaft torque, that is output power into 60 by 2 pi m, that we all know the shaft torque, because output is related with the shaft. So it is 18 into 10 to the power 3 into 60, that is the output power, by 2 pi into 1440, that is 119.36 Newton meter. The gross torque, that is Tg equal to Pm by 60 into 2 pi n. Shaft torque is related with the output power, and the gross torque is related with the mechanical power that is developed, Pm, that is the mechanical power. So Pm into 60 by 2 pi n. From the mechanical power, if we deduct the windage and the friction losses, we will get the output power. From that equation, it is clear. This loss is deducted from Pm, we will get the output power. So the shaft torque is related with the output power, because we know torque into omega equal to angular speed equal to the power, and the gross torque is related with the mechanical power developed. So Tg equal to Pm into 60 by 2 pi m. Just put the values of Pm, 18.5 into 10 to the power 3 into 60 by 2 pi into 1400, that is 122.68 Newton meter is the gross torque Tg. So today we have learned about the working principle of a three-phase induction motor, synchronous speed, slip, torque slip characteristics, power flow diagram, the losses, different losses that we have calculated, and the efficiency of a three-phase induction motor. And along, we have done some numerical problems to understand all those topics that we have learned today. Thank you.